Hello and welcome to another Great Cow BASIC tutorial. This is part 15 for the PIC18FxxQ41 chipset. We're getting well into the lockdown, another set of lockdown videos. Here we're looking at pulse width modulation to control the LEDs. We had previously looked at pulse width modulation back at tutorial 10. But we're going to peel that back a bit further and show you some more capabilities within the microcontroller, but also the software to make it easy for you. Let's get cracking on. We have a microchip low pin count demo board. It's the green one. I can show you that in the lab. It's here, it's sitting there, it's the other way around, and it's flashing the LED. And the important thing is that Microchip have contacted me, and I will be getting some Curiosity Nano boards, and I will do another video once I get it. Okay. So the layout I'm using so that you can reproduce the low pin count demo board. You can copy this, and I'm just going to be flashing these LEDs. And this is by Chris Roper. And any questions on this, get back to us. Just ask. Anything you need. So what we're going to be doing, we're going to be making the LED flash. We're going to be changing the duty and the frequency to make the LED react to light. And we saw very quickly in the lab there that there's something happening to the LED. Okay, and we'll discuss how we control the frequency, which is essentially the next on and major off cycle, and then the duty is actually part of that. Now, tutorial 10 goes into this in greater depth. I'm going to be very specific about the code today. So it is simply a succession of pulses. It's just a method of reducing the discrete number of components that you need, and it is used for delivering electrical signals. We're going to use an LED, it could be a motor. And it gives you an average as per the little diagram there, and I've discussed this in number 10. And we'll see that shape in the oscilloscope. So if I go out to my oscilloscope, there is an oscilloscope on the screen now. There's an LED flashing on the demo board, and you can see there is a square signal that's happening. And so what we're doing, we're turning on and chopping up the signal on and off at a specific frequency for a specific duty value. My setup today is I've reverted back to the oscilloscope, and you can quite see from the lab there that I've got a couple of wires connected, and we're going to monitor really one. It's just the one. The only one you need is CC on RC0, and we're going to see that square wave come up as we change the parameters. So let's have a look at what different types we've got. I can think of 4 different types easily. There may be others. Let me just walk you through these. Okay, so there's number 1. There's a software wave. We can do a software which gives us a number of pulses, and for that you don't need any PPS. And it can be any valid output port. And so you can tell it the duty, that's the on and off cycles, and you can tell it how many pulses. And this is very useful for particular types of interfaces. They may say, send 10 square waves. Then use the software way. We'll have a look at that. There's a second way, which is using the CCP PMW functionality, but this is giving you a fixed frequency with a fixed duty that you can turn on and off at any time. Okay, using a particular timer. I said timer 2, but you do need to use pulse width modulation. It's low impact code. It means it doesn't have a lot of code, and there's 2 constants. It uses some scripts inside of a Great Cow BASIC. There's the third method, which you've already seen, which is just variable frequency, and we were using a variable duty with timer 2, and we're changing the duty, if you remember, via the ADC. And you will need to use PPS. So for that, see tutorial 10. Finally, the 4th one I could think of was the new 16-bit module inside of this specific chip. Wide range of capabilities, much greater than the CCP Pulse Width Modulation above in number 3. But you do have to use PPS, and there's lots of parameters to set. And I'm going to show you how you can really enjoy using Great Cow BASIC and the data sheet. Okay, so let's have a look what we're going to do. We're going to walk the examples, and then we're going to view it in the scope the whole time. Okay, all right. Let's get started. So let me just go through what we've got on the screen here so that your screen is slightly different from what I'm seeing. So I'm just going to walk the screen. You can see a picture of me here. Great. You can see the code on the left. You can see in the middle the oscilloscope. And then you can see what's actually happening on the LED at the same time. So I'm going to walk the code on the left, and then we're going to see what's happening. Okay. All right. So this is number 1, which is the software way. And typically I've got the chip statement, which you've seen before. I will update this to put option explicit in because that's very naughty of me. Option explicit, we have that in all our code. I have a standard header here that you've seen before. I am not going to discuss that. So let's go directly into the meat. There is a command in Great Cow BASIC that's called Pulse Width Modulation, PWM out. You can have a number of channels. I'm going to be using channel 1. It's an arbitrary number in terms of the port as well. So you can say, right, I want PWM out on port C0. And what I want a cycle of 127. And the range, as you remember, is 0 to 255. So for a duty cycle of 50%, I would put 127. And I want it for 7 cycles. And you can see that on the oscilloscope. If I change it to 5, I'm just changing the parameter here. So I'm saying, just recap, PMW out is going to use this constant here, PMW underscore out 1. It's hooked up on port C0. So I'm going to change that to RC0 to match our constant at the top here. And I'm going to say to it, turn it on for 100 milliseconds. A duty cycle of 50 equates to 127, 5 pulses. Program. You'll see the programming event on the screen there, and we will see the oscilloscope change to 5 pulses. It is 5 pulses. I can change it to 3 pulses. This is very useful for having sequences required for certain accessories. 3. So, the frequency is dependent upon the chip frequency, but it's very useful. Number 1. Let's have a look at a second method. I'm just going to comment that out and get it out of the way. Okay, all right? Because there is a second method I've got in here. And this is called fixed frequency and a fixed duty. We use a couple of constants, and it says PMW frequency is 1, that's 1 kilohertz, and a duty cycle of, I've put 90%. I've done that for a particular reason. Now, and to start this one, we say PMW on. So we just set these constants and we turn it on. Let's program that up, and then we're going to see what happens. Nothing. And that is quite correct, because you remember in the table we said that we needed PPS to make CCP PMW work. Let's go into PPS and make that work now for us. So I'm just bringing up PPS tool here. I'll clear it down. Let's take channel 1, CCP1. We're going to put it out on RC0. Add it in there. We'll put it in on RC1 as well, and we'll leave the other 2 today. Copy. And I've taken that into my copy and paste buffer. Back into my source code. I always add it at the top, other people don't. Put it here. Press F5 to program it. And we will see on the oscilloscope we get a fixed. We've got 2 LEDs, which is quite correct, and that is flashing away because I just need to change the frequency of my oscilloscope software. Okay, if I can find it. There we go. 90. Look at that. 90. Let's go back into the source code, and we'll change that to 50. Where is it here? I'll change that to 50, change my documentation to 50 and program it, and you will see that the oscilloscope will change the duty accordingly. Well, that's because I didn't change it. I put it to 95. Who do live demos? So key here is 2 constants and PMW on. There are other options for different pulse width modulation channels, but this is the basics, and it's all in the help. But very simple, and that took us, that's 86 words of RAM of program memory to make that work, and let me rest assure you, that is very few to get that square wave out. That is built into the libraries of Great Cow BASIC. So what we've done there, let's go back into PowerPoint and look at that table that we were looking at earlier on. I'm just going to bring up the right screen. We've looked at the software way. We've looked at number 1, done that, tick. We've looked at number 2, fixed frequency and fixed duty. It did require PPS, I proved that to you. I'm not doing number 3 today because you can go back to tutorial 10 and see that. Now we're going to take a very different tack with respect to pulse width modulation, 16-bit. Let's go into the code and we'll see what we've got. Well, it's very different. What I'm going to show you here is how you can do this. You can use Great Cow BASIC without all the fancy codes. You can just write to the registers to make it work. So we are going to go into PPS tool and we're going to set it up exactly as we normally do, but this time it's a PMW channel. So we have to go into PPS tool. Look. This is what, and in PPS tool, I'll clear it down. We can see in here, look, we've got a number of channels here called PMW, 11 through to 32. I'm just going to take number 11, okay? And I'm going to plumb that into, connect that into RC0 and RC2 again. RC1, 0 and 1. Take a copy. We need to do that regardless, okay? All right. And then back in my source code, I'm just going to hook that in, and then I'm going to show you what I've done. Hook that in. I've now got 2 channels set up. I could have 4, whatever, doesn't really matter, it's arbitrary. Let's just zoom in on there for you. I've added that in. Standard header here, I'm not going to go through that. Look at this. I've got a load of registers. Where did that come from? Well, let's go out to PPS. Let's go out to my desktop for a second. And I'm just going to look in PIC-info, and I'm just going to open up the data sheet. So it opens up the data sheet. And in the data sheet, if I do a quick search for pulse width modulation, I end up with a specification saying there's 3 of these. And if I keep going through and I go down to page 451, I can find a manual. Look at that, the section on the pulse width modulation. It's a 16-bit PWM module. The outputs can be sliced, then it can be left aligned, right aligned, center aligned, interrupted, compared. It's absolutely fantastic, okay? But to set them up, you need to set a number of registers. And those registers are at page 475, and there's a whole page of them. But let's not scare ourselves too much, right, okay? Because normally we mask this from you, but I'm not going to today. There are 3 different sets in here I can see, and if I look very carefully, they're in banks. So if I look at that there are banks of these that come down to, I've just taken a cut and paste there, let me just bring it up for you. There was a bank of them. So there are only a number of registers that make this work, and you have to go through the data sheet in detail, but what I've done is give you an example in the source code to show you how to do this, okay? So if I zoom back in here, there's a set of registers, and they directly relate to what's in that picture we saw previously. So if we look at that desktop, PWM ER1 here, and we'll see them you'll see them appear in my source code exactly in that order. So you could work through and understand how this works. But I'm talking directly to the registers and the register bits this time. I'm not using a library. I'm just showing you that you can do this by hand if you wish. And let me just show you I've got no other code. I've got a do loop, so I've set up a series of registers with a series of parameters to give me a specific frequency and a specific duty. Let's have a look what it's done in 16-bit. And sure enough, I have it on my oscilloscope. I have already gone in, I've calculated with a pen a 1 kilohertz signal at a duty of 50%. In the source code, I've then come into here and I've actually then recalculated this for a different duty. I program that. I'm writing directly to the registers now. Okay, no libraries involved. And now I've got a duty of 25%. Well, now we know that you can do this. You can actually do some clever stuff in Great Cow BASIC, because you can create a variable that talks directly to the two addresses or two registers that control the duty cycle. Let me show you. Down below, I'm just going to take out my do loop because I had to prepare this because I had to think about it. I've created a word variable called ADCVal, and I've created an alias to the two registers that I've just changed up above. And then I'm simply saying, give me rotate through the that particular value, just incrementing through one at a time, and it will change ADC value from 0 to 3 FFFFF. And I stop and start the Pulse Width Modulation module, and you will see what happens. So I've used an alias to talk directly to the two registers. And you will see on the oscilloscope and on the LED, I'm getting a signal. That is done in 160 words of code. And my oscilloscope here is the issue. It's just not fast enough for this. Let me just see if I can improve the view there. Oh, that's a bit better. But you can see that cycling through quite nicely, and the LED actually on the screen. So what I'm showing you here is that you can write to the registers directly. You don't need to have all the libraries. You can use aliases to point to word type registers where you need to join them together. And you can use Great Cow BASIC as a mix and match between the two. Tomorrow, we're going to look at some assembler to see how this actually works underneath the in the engine itself. Back to PowerPoint. So let me just get rid of my ink. So we've looked at the 4 different ways, and we've had some great, it's quite an insightful methodology to use the 16-bit. It shows you that you can write direct to registers, and that all Great Cow BASIC is a means to an end to get that register updated. Okay, so what I wanted to show you was Pulse Width Modulation. I've shown you a very simple way to generate pulses, simple way to generate fixed frequencies, and a more sophisticated way to get the 16-bit code operational. Tomorrow, we're going to look at updating memory in terms of prog memory and a thing called SAF, which is similar to EEPROM that we looked at number 12, but they have different commands, and we just need to look at them and then we'll do a close out over the next couple of videos. Okay, with that, I will love you and leave you. Enjoy.